Is
coming
it
up.
better? Yes. Is it big
It's
enough?
coming up.
Okay.
Yes, it's up. You can go ahead, sir. Go ahead.
All right. Thank you so much. And I don't know whether I should start from the beginning, but I'll just maybe quickly, yeah.
Yes,
I'm presenting
please.
on behalf of Prof. Tangana, and the title of the presentation is Reproductive Momentum Unleashed, Harnessing Second Order Dynamics to Decode Epidemic Waveforms and Predict Spread Patterns Beyond R0. This is Prof. Tangana's work, and I have the privilege of presenting on his behalf as Prof is detained at the World Lawrence Summit in Dubai. I think he's also presenting today. He did send his deepest regards to the conference and his sincere apologies for his absence. So, um, as I've mentioned, the title of the presentation and the next slides we discuss the practical gap, what we want a new number to achieve. So the new number, wait, okay. Oh, I think the first slide is limitation of the reproduction number, the traditional reproduction number that we know. And normally we do that in epidemiology. That's what we do, the R0. So it is one of the most used number, or in most of the studies will use the R0, where we know there's a condition for it, whether we want to know whether there's going to be, if one person is infected, will in a susceptible population, will that one person cause more infections, or will the pandemic die out if there's one person infected? So, so we begin with a critical examination of the fundamental concept, the basic reproduction number, and its effective counterparts R0, RT. And then we know that these metrics are indispensable for determining inversion potential and providing an instantaneous snapshots of transmissibility. Okay, so however, for forecasting and intervention planning, the limitations are significant because R at T is inherently a first order matrix. It quantifies the present velocity of an outbreak, but provides no information on its acceleration or trajectory curvature. So it cannot distinguish, what we basically say, it cannot distinguish between epidemiologically divergent scenarios, something like that. All right, so the gap that we're going to discuss or wanted to achieve, it should be able to detect directional or reproductive momentum, or to see whether there's the epidemic spreading up or slowing down, or ahead of the visible case surged, and also predict wave type, whether is it monotonic or isolatory, and also flag resurgence earlier than RT threshold allows. All right, and then also embed delay effects and trajectory curvature. So it kind of interventions that can be timed to prevent large asymmetric wave. All right, also provide a compact dimensionless signal usable for operational surveillance and early warning without discarding the intuitive of R0. Okay, so the the damping oscillation. So rather than treating the epidemic trajectory simple as increasing or decreasing, we gain an insight by viewing the effect of the curvature of the infected component. Remember, in an SIR model, this I will be the infected component, right? Component. So we start with the susceptible, the SI model, we start the susceptible, infected, and then the recovered. So the I will be the infected component. So we treat this I at t as a damped oscillator, a system whose future motion depends not only on its current level and velocity, but also on its acceleration and curvature. So the highlights is that I of t plays a role of a displacement. Signals whose velocity is instantaneous growth and the k slope. And then acceleration also captures the change in the slope, whether the epidemic is spreading up or slowing down. And then the damping term models law mechanisms, behavior change that reduces amplitude over time. A restoring term model for forces that pull the system back towards the equilibrium or perceptible replenishment or contact structures. So why this view matters? It matters because acceleration and curvature are predictive. So they contain information about upcoming turning points and the likely shape of future waves. Okay. So, so we know the mathematical intuitions and practical consequences. We know the second order presentation. So the first term here, we'll have acceleration, second derivative. First derivative will have the damping term, then the first one will be the restoring term. So of course, the alpha will be um, the loss or control of strength, and beta will be the infection potential of the susceptible pool. Those are the two parameters that we already familiar with. And the sign of the characteristic determinant, which is D, determines the dynamics. So if D is less than 0, we know that we have oscillatory, which is a wave-like response. And then if D is greater than 0, or equal to 0, greater or equal to 0, we have an overdamped or monotonic return. So we need to monitor or monitoring only the I or the first derivative of I, it misses the lantern acceleration. Early positive acceleration warns of an coming surge before cases visibly arise. So traditionally, we'll only monitor these two. All right, so what we have now is the bridge, what we bridge, the gap that we bridge here is that we have a paradigm shift. Rather than viewing the epidemic incident curve merely as a time series, we reinterpret it through the lens of second order dynamics. That's the gap that Prof here was trying to cover. So so the model incidence I t by damp oscillation is given as that. I've already explained that the alpha will have this parameter alpha and the beta as well. So equation 1 becomes the equation 1 focuses attention on acceleration in addition to the instantaneous rate of change, which is the one that would use the first derivative, oscillatory solution, natural response to epidemic waves. So what we have now is what we call the RMI, which is to translate this theory into a practical surveillance tool. It was proposed argumentating the effective productive number with a momentum term. So one proposed form is the reproduction momentum index, which is this one, where alpha lambda is an scaling constant covering sensitivity of acceleration. This value here, okay, and then R of t is near 1. So R of t is near the critical threshold of 1. a significant positive acceleration can elevate RMIT, this term here, and then above operational threshold, providing an early warning signal rather than R of T alone. So this embeds the predictive power of the second order dynamics into a familiar index. So consider the following SIR model that we know, normalized with n equals to 1. So we'll have it in this form. So the dynamics, this term, this variable, this parameter here allows the possibility of an endemic equilibrium. So this is a case where we have I is greater than this equilibrium point is greater than 0. So it opens the door to sustained or damped oscillations around the equilibrium point. All right, so what we see here is that, let's say this is the case where, let's say SIR equals to 0, then we try to solve for the endemic equilibrium points. Then we linearize the S and the I subsystems about the equilibrium point. Then we have this Jacobian matrix. So this I'll just pass through because I know most of you are very familiar with this. And then we see that the values of A and B will be given by equation 12 and 13. So the connection, the connection phrase, this pair, A and B, plays exactly the role of alpha and beta in the damped oscillatory. Their values determine whether perturbation spiral or decay monotonically. Okay, so let's look at that. If we have an example here, with those endemic equilibrium points that we have discovered in equation 12 and 13, we see that, let's say you have, this is the term that we'll have, 15. If we have the parameters, alpha, mu, and beta, then S will be 2.25 and I will be 0.37. And so if we compute the discriminant pieces, we have the following values. So that we can conclude that 0.16 is less than, only given there on equation 18, is less than 2.4. So we are literally following the equation 15 there. So we have that the discriminant is negative. Okay, so if the discriminant is negative, we know the cases that we have there are 3 cases. The closed form solution of the perturbation. The first case, if this is greater than 0, we have real distinct roots. And if this is 0, we have double roots. If this is less than 0, we have complex roots or damped oscillations. So case 3, we can see that it yields a familiar exponentially damped sinusoid. Okay, so the Atangana strength number. So now we are going to discuss the Atangana strength number, which it's a dimensionless index constructed from the coefficients of the linearized characteristic equation of the disease model. So the Atangana strength number quantifies the balance between application and damping and provides a compact criteria for wave generation. So the first step, we formulate the disease model. So suppose you have that differential equation where X collects all the compartments, and X donates the model parameter. So X of X and this X. So you have all the compartments and then the model parameters. So the second step is to identify the master classes. So we select the minimal subsystem that governs the infectious dynamics, so which is the SI subsystem, and then denote the master variables governed by that, and then determine the equilibrium which we did just now with the SIR model that we know. Okay. Now we linearize the master subsystem about the equilibrium point, and we let Y to be U of T minus U star, and linearize the dynamical system, which will be of this form, where J is our Jacobian, and if the master system is two dimensional, the stability of U is determined by the eigenvalue of the Jacobian. All right, so now the eigenvalue satisfy this, just to satisfy this characteristic equation. And then for a two-dimensional Jacobian, we have a quadratic polynomial of this form, equation number 31, with the real coefficient functions ax, bx, determined by the trace and the determinant of J. Okay, now, if b of x is greater than 0, we assume for epidemiologically relevant regimes that it's a positive feedback product. So we define the next step, step 6. We define the discriminant that by this component, equation number 33, a squared of x minus 4b of x. So the oscillatory linear response arises when this determinant is less than 0. So the complex conjugate eigenvalues. So the Atangana strength number is given by a squared into x divided by 4b into x. So, of course, it follows directly from this form that if this delta is less than 0, if and only if a squared minus 4b is less than 0, which also implies that a squared over 4ab should be less than 1. If we assume that, of course, like I said here, assume that b of x is greater than 0. All right, so the interpretation of the Atangana strength number. So it is dimensionless and compares the squared damping like terms, a square, to 4 times the restoring like term, which is b. So if at is less than 1, it signals a parameter regime where small perturbation produces isolatry, or the waves like decay or sustained circles if non-linearity allows. So Atangana strength number is not designed for time delay differential equation. You do not apply the delay-free Atangana strength number criteria when explicit delay appears in the model formulation. Okay, so let's look at this example. If we have a system of this form where we define a of x as the following and b as the following as well by question 36 and 37. So where our mu is the vital rate and gamma is the recovery rate and k is the extra removal or control parameter. So then the Atangana strength number will be written as follows, following from equation number 34. So if we put everything there together, we get that. And so the wave generation is predicted if this condition is met, as you saw here, that we need to have this term should be, the Atangana strength should be less than 1. Okay. And then for the model where A and B depend on equilibrium quantities, let's say the endemic equilibriums, one obtains the relevant representation, which is given by that. So remember the equilibrium points we had for the SIR case. So this will be the Atangana strength number. So it will be under this mapping where A to be beta of I plus mu and B will be beta square SI. So this form highlights how equilibrium point, prevalence, and susceptibility modulate the orthogonal strength number. So if we have a low S or a high I, change the balance, and thus the wave, we have a wave potential. Okay. So, hello? Okay, in summary, so the orthogonal strength number provide a compact local criteria. Hello?
Go ahead, sir. Go ahead, sir.
Okay. So it predicts the oscillatorily linearized systems, and then also secondly for computational flow, for computation flow and standard chain. So you have a model, the master classes, the equilibrium, the Jacobian characteristic polynomial, and then the orthogonal strength number. So the orthogonal strength number supplements but not replace conventional diagnostics like the R0. It supplements, it does not replace it. It specifically highlights acceleration-driven wave potential. So you need to use this strength number with caution, because it is a linear equilibrium indicator, and it is invalid in a delay-driven formulation unless derived appropriately. Okay, so this will be the procedure that one has to follow when you are dealing with, you want to apply the orthogonal strength number. So if you have an ordinary differential equation, then you have to identify the master subsystem. You compute the equilibrium point and linearize, and you do your Jacobian, the Jacobian. Then you obtain the trace, the determinants, and then you can compute the orthogonal strength number. So if we have, for instance, you have a system with demography. So you have a model of this form, same SIR model. So the master subsystem will be SNI. So the endemic equilibrium point will be, of course, where I is the equilibrium point of I will be greater than 0. So this will be the equilibrium points, and the Jacobian related Jacobian to be of this form. Then our trace will be given there by the trace and the determinant will be given by equation 47 and 48. So same applies if we have a system of this form, the SEIR, which is the susceptible, exposed, infected, and recovered. So if you have 4 compartments, so here this will be your master subsystem, E, and the exposed and the infected group. So in this case, your equilibriums will be given by that, and your Jacobian will be given by 55, and then your trace and determinant will be given by 56, equation 56 and equation 57. So the strength number in this case will be given by the following equation in equation 58. All right, and then if you have a SEIS, this is also a bit similar, but so you'll have a Jacobian of this form, and then with the A given as this, B given as this one, so is C and D, and then the characteristic polynomials will be given as follows, equation number 61, and then the orthogonal strength number follows also to be in this form. Of course, we know the values of A, B, C, and D, which are given the equation number 60. All right. Now, same applies with SIR, S. So you'll obtain the Atagana strength number in a similar fashion. All right, so what happens now if you have a perturbation form and the three regimes? So the perturbation equation of infectious perturbation, I, it will be given as this form. Then it has a characteristic polynomial of this form, and then the Tangana, we have defined it to be this. So the three regimes will be, if this is less than 1, we have underdamped wave. If the Tangana strength number is equals to 1, we have a critical damping. And I don't know, my slide is not showing. So the first case, if the strength number is less than 1, this is the case where if A squared is less than B over 4, so the roots are complex. So the biological interpretation of this will be, we have repeated epidemic waves with decaying amplitudes. So this will be the biological interpretation of the first case. All right. The second case, if the Tangana strength number is equals to 1, we have a critical damping, which means we have double roots in this case. And then this just mean that, so we have fastest non-oscillatory return to equilibrium. At most one prominent peak, then monotonic decay. Okay. So then now the third case is if it's greater than 1, we have two distinct real roots. So this means we'll have a monotonic return. So there won't be any other waves. So we have a strong damping dominance restoring forces. All right, and then so the practical notes for applying the Tangana strength number. Of course, the first one is that the Tangana strength number is a local diagnostic. You pair it with the nonlinear smart simulations for global behavior, and you estimate coefficients A and B, either from the model linearization or by short window fitting of observed the compartments S and I dynamics. So you always have to present the uncertainty bounds. So also another one is that it complements, like I've said before, it complements the reproductive number, which is the R0. So R0 answers the invasion potential, and then a Atangana strength number, it partitions post-invasion dynamics into isolatory or monotonic regimes, essentially for intervention timing and preparedness. Let's say maybe if you have an outbreak and all that. So we study whether the Tangana strength number can be used to detect the half bifurcation in polars in planar systems by monitoring the trace and the determinant of the Jacobian All right, so we have to say we consider this planar Jacobian depending smoothly on the parameter mu. So we have that Jacobian there with the following trace and the determinant. So in this case, the Tangana strength number will be given by equation number 79. So now what do we claim here? We claim that if the half bifurcation occurs at mu c, then our trace will be equal to 0, the first case, or the determinant will be equal to 0. This will imply that the Tangana strength number will be 0. So we also have transversality, reduced to this point, dt over du should not be equal to 0. For mu near this value, mu of c, the orthogonal strength number should be less than 1. This one implies that we have complex eigenvalues and the orthogonal strength number approaches 0, signals approach to the half bifurcation. So if you have then you can have the first step, of course, you get the eigenvalues and the discriminants. So, and then also the classification that if the determinant is less than 0, you have the complex conjugate eigenvalues. So you'll have a focus or spiral, and then so equation, we look at equation 82. So that's the case what the orthogonal strength number implies, if and only if the determinant in this case is less than 0. And then also equation 79, we have the following in this case, that the orthogonal strength number in this case it will be 0. So so the other case also is that we'll have that the monitoring orthogonal strength number, which is given by this near u mu of c approaches 0, occurs when t approaches 0, non-zero dt over the mu ensures that the orthogonal strength number crosses through 0 linearly unless the determinant simultaneously vanishes or is excluded. So let's consider this worked example. If you have that dynamical system there given by 87, then the Jacobian at the origin. So we have our t and the delta given by 88. So the orthogonal strength number in this case is going to be given by equation 89. Okay, and then so now let's see the practical implication and the usage. Okay, so for detection, we track this value, the orthogonal strength number, along a continuation path. So the strength number decreases if the determinant is greater than 0, efficiently flags the half threshold. And then also we have precursor signal and caveats. And what here I can mention also is that the orthogonal strength number evolution complements the standard bifurcation analysis and provide an intuitive scalar monitor for approaching oscillatory instabilities in planar and epidemic models. So we addressed two questions at the equilibrium point. The first one, can the orthogonal strength number recover the classical inversion threshold using given or usually given by R0? So can the orthogonal recover the classical case, which is the reproduction number R0? So okay, and then the second question is, under what exact condition does the orthogonal strength number give the same outbreak or die out signals as R0? So the approach is to linearize at the differential the DFE form the infection block characteristic polynomial, compute the orthogonal strength number at the disease-free equilibrium DFE, and compare its sign or behavior to that of the reproduction number, which is the R0. Okay, so in this case, if we have that system that we saw earlier on, so we know for sure, in this case, the reproductive number is given by this. This is, I'm sure most of you are familiar with this already. So if we linearize, some of this stuff I can't really clearly see. If we linearize and follow all the steps, and then we try to compute the diagonal strength number at the disease-free equilibrium, we have the following equation. And then for the second case, for the SEIS, this is what we have. The reproductive number will be given by this. And then in terms of the diagonal strength number, it will be given by equation 106. So we do the same also for the SIRS, and we see also that this is where the R0 will appear there in equation 110. So we conclude that R0, if R0 is greater than 1, if and only if the diagonal strength number is less than 0. Okay, and then in this case also, I think I didn't discuss this one. We concluded that R0 will be greater than 1 if and only if the diagonal strength number is less than 0. All right, so we have this table here. Remember the cases that we have considered: the SIR, the SEIR, the SEIS, and the SIRS. So these are the all well-known reproductive numbers. And then the diagonal strength number or associated to the SIR, we just discussed also, they are given here. So the condition is that if R0 is greater than 1, then it implies also that the diagonal strength number will be less than 0. If R is greater than 1, the diagonal strength number will be less than 0. If R0 is greater than 1, then it will be, the diagonal strength number will be less than 0. And for this case, if R is greater than 0, we will have that the diagonal strength number should be less than 0. So now the interpretation: what or when does the diagonal strength number match R0? So R0, if it's greater than 0, if it's greater than 1, we know that the diagonal strength number has to be less than 0. So the reason for this is that infection block or determinant flip sign at the invasion threshold. So the algebraic manipulations express the diagonal strength number in the form of proportionals to R0 minus 1, 1 over R0 minus 1, or R0 minus 1, reproducing a negative diagonal strength number when R0 is greater than 1. So practical implication means that the diagonal strength number that we evaluated at the equilibrium points recovers the classical inversion sign for these models. Therefore, the diagonal strength number can serve both as a wave pronacency index near equilibrium equilibria and as an inversion indicator at the disease-free equilibrium via the signs, of course. So anyway, we have the limitations and the recommendations. In conclusion, we see that Provatangana's work introduced a formal framework based on second order dynamics and proposes the strength number and as a novel dimensionless epidemiological diagnostic. So interpretation depends on the value of ASN, diagonal strength number, and also the local diagnostics for strong nonlinearities, multi-stability or explicit delay, complements the diagonal strength number with nonlinear simulations, normal form calculations, or delay aware analysis. So So the bottom line here is the Tangana strength number unifies inversions and wave, as I mentioned before, but the interpretation must respect the evolution point, okay, and the model structure as well. And then this will be the case from our 4 canonical models. We obtain the following: that if the Tangana strength is less than 0 and the reproduction number is greater than 1, we have an outbreak. And if this Tangana strength is greater than 0, that means the R0 will be less than 1, then the disease die out. And the Tangana strength number, as it goes to positive infinity, then R0 will be equal to 1, which is the threshold. So the Tangana strength number condenses both the inversion threshold and the dynamic model into a single compatible scale. So in essence, R0 answers can inversion occur, and then the Tangana strength number, it answers how will it unfold. Is it going to be a wave or a monotone, a growth, or a decay? So I think I'll end here.
All
Hello?
right, thank you very much, Dr. Hans Magau. Let's put our hands together for him. Okay, Magau, all right. Macau, all right. Macau. All right, I don't know if there are questions for him. We just want to take one question. I will proceed. One question. Okay, all right, I will take 2 or just make it snappy. 2, we'll take 2, then move to the next item on there.
Yeah, Dr. Hans, well done. Thank you for
Magau.
the presentation. Okay.
Yes, thank you.
Okay, Dr. Magau, well done. So, okay, the question now is this: epidemiologically, reproduction number, particularly the basic reproduction number, by definition, has to do with the expected number of secondary cases that one infected individual can produce in an entirely susceptible
Yes.
population throughout its lifetime, of being infectious. So now one will be interested, and then with all that we have been able to do with basic reproduction number, and then also effective reproduction number when the population is not entirely susceptible. With all that we have been able to do in epidemiology with that threshold quantity. Now, what has the ASN come to bring to the table in terms of this epidemiological insights, in terms of having to determine herd immunity value threshold, in terms of having to determine when the disease dies out? Does it mean that the reproduction number is not able to capture these things effectively? And if yes, what other insights would this ASN be able to give regarding these epidemiological concepts? Yeah, thank you.
Right. You can go ahead and respond, sir, Doctor.
Oh, there's only one question. Okay.
Yeah,
Okay.
no, there's another one. Respond to this. You could respond to this, sir.
All right. No, thank you so much for that question. If you had checked the presentation, I think somewhere here, yeah. So it's not it's an extension of what we already know with the threshold number, but in this case, it can have many applications. For example, because remember we had said that the first one, it answers R0. We know that can we have will the spread become an endemic? Is it gonna be uncontrollable or not, so that we can advise the government or advise those in health sectors to control the disease, right? So it acts as a parameter that tells us, is this worst case going to happen, or will this thing die out? So the Atangana strength number, when it comes to disease modeling, it gives you it tells you more than just will the spread will the disease spread or not. It also tells you, remember with that acceleration term, it tells you, okay, at what acceleration is it going to be a wave, possibly how many waves occurrence, or is it going to decay later on, and stuff like that. I don't know if
Okay.
that answers.
Okay, all right. Thank you. The next person.
Right. Thank you very much, Doc, for the wonderful presentation. I want to
Thank you.
ask
Yes.
2 questions. One
Okay.
is the connection of this TSN with the global analysis and the backward verification, because I think those 2 are very important in disease analysis. So what do we do? I know that anytime in an endemic area, if we are carrying out analysis, we consider the global analysis and the backward verifications. And the second one is on the steps, just a little, so that we see again how you linearize the system. Thank you.
All right. Doctor, you could go ahead and respond, sir.
All right. I didn't really get the second one. Can you maybe repeat the second question? Sorry about that.
From the equations you have, how do we move from that place to using the TNS number?
ESN.
TSN. Anganan strength number.
ASN.
ASN, yes.
ASN.
It's okay. Thank you.
Strength. Go ahead,
Okay,
sir.
so
Yes.
okay, all right. So I think I'll start with the first one. Thank you for that question. So the local bifurcation with the Atangana strength number, it has a direct one-to-one correspondent with the conditions for transicality and half bifurcations. So I think it's an excellent tool for locating these parameters in space, and in global dynamics or global analysis. So the Atangana strength, I think for my side, it has an indirect but virtual connection. So it identifies the local dynamics regime, which is the building blocks, of course, for the global behavior. So the second question, I think it depends on the applications of what you are doing, because generally the strength number is just to say, if you have, because the motivation around it to say we are trying to be as practical as possible. Because remember, if you have R0, it will just tell you, is it going to occur? Are you going to have an endemic, pandemic or not? And then it only gives us that value. So now this one is a different an extension to the framework to say, beyond what we can get from the R0, what else can the dynamics at play give us? And it will definitely depend on the study at hand and what questions I'm trying to answer. So it will work as a governing parameter as R0, depending on the parameters as well, whether if we change this, what will happen, and of course it will have a lot of applications in epidemiology as well, because it will answer more questions than just getting, okay, then there's going to be an endemic, pandemic, or there won't be a pandemic. So it will easily tell us, okay, fine, if this is the case, is it going to be um, um, uh, how long will the pandemic last? Something like that. Are we going to have a wave or one wave, then later on things are going to go back to normal? So I think it's a framework that one will need to explore deeper as well. And thanks for that question. I hope I did touch on what you were asking.
All right, thank you very much, Dr. Magao, for that presentation on behalf of Professor Upton. So I want to give a remark. I'll invite Mr. Lashipo to do that. All right, sir.
Okay, thank you so much, Doctor, for that presentation and for the time spent to engage with us here. I want to believe that it's just that Professor Bakari stepped out now. He would have loved to speak himself for the kind of relationship I think he has enjoyed with Professor Ntaganda. And then as a center, we have really had a very good time with Professor Ntaganda in most of our engagement. As you can see, ACM is one of the association we both belong to, and you see that down there that there is this African Society for Industrial and Applied Mathematics called ACM, which is an association we would like to encourage all of us to join. I think Prof is coordinating the West African region of that association. And I believe that with more collaboration, we as Africans can do much more. So I want to say thank you for your time, and we hope that we see you next time, and extend our greetings to Prof. We appreciate your time. Thank you so much. Can we please appreciate him? Okay, now before I hand the mic over to our program moderator, I would just like to plead with us, both the online and physical people who are physically present. I've said it the other time that we didn't start the way we were supposed to start, and we were waiting for many of us. So for that, you can see that our time is obviously not at what it should be, based on what we have on the timetable. So the next presenter is already waiting. Professor Etienne is already waiting. In fact, he has been waiting for very long, and we would like to take him. And after that, we then go for our lunch. After which, we still want to create time for the parallel sessions to really be robust. So for that, we feel that we may need to push the time a bit again for this today. Also, and we want to use the opportunity to plead with us. Please, we are to come here, arrive here 9, so that we settle down and we're able to take a recap. And by 10 on the dots, the presentations starts. So that's the ideal thing. But then if you come late and the presenters are not on the seats, it may delay our activities. So now we'll be going to the next presenter, Professor Etienne Badu. I will now hand over the mic. So online presenters, please stay tuned. After the presentation of Professor Etienne, we will go for lunch in this place. And then after lunch, we'll return for a parallel session. Hopefully, we'll be able to take that. Or if not, then that means we take the last presenter for the day. And then after that, we now have we have a time for a parallel session that will take as many people as possible. So we are trying to adjust our time here because of the time people came in. All right, thank you. I want to believe the information is passed to the people online now who have been asking many questions. Thank you so much.
Thank you very much. All right, so I'll be inviting Ms. Olorunfemi to read this edition of Professor Etienne. All right, let's put our hands together for her.
Professor Etienne Pardo is a renowned French mathematician and professor emeritus at AIS Marseille University. Internationally recognized for his pioneering contribution to stochastic analysis, while he is not known for his aphorism or philosophical quotes, his influence is reflected in the extensive citation of his work across mathematics and applied sciences. He is best known for introducing backward stochastic differential equation in a seminal 1990 paper with Xi Peng, a development that has become foundational in stochastic control and mathematical finance. His earlier work established key existence and uniqueness results for nonlinear stochastic partial differential equations. More recently, he has applied stochastic modeling frameworks to population dynamics, evolutionary biology, and infectious disease modeling. These contributions are further consolidated in his influential books published by Springer and Wiley, including stochastic partial differential equations, an introduction in 2021, probabilistic models of population evolution in 2016, and Markov processes and application in 2008. Join me and welcome Professor Etienne.
Okay, hi.
Go ahead.
Thank you very much for the introduction. I hope you can hear me. Okay, let me.
Yeah, I'm hearing, sir.
Let me share my slides. Okay, so I hope you see the slides. So I'm going today to talk about an epidemic model of malaria. It's a very, very recent work, which is not fully finished right now, but I will. Oops. Excuse me. Okay, so so thank you for the invitation, and let me try to share my thoughts. Okay, so as you know, and there has been already talks on this topic in the conference so far, malaria is a very severe illness which affects currently around 250 million people in the world, mainly in sub-Saharan Africa, but also in South America and Asia. It is responsible for 600,000 deaths every year around the world. So, malaria is a contagious disease, but unlike many other contagious diseases like smallpox, measles, etc., malaria is not transmitted directly from human to human. As you know, a susceptible human gets infected by the bite of an infected mosquito, and a susceptible mosquito can get infected when biting an infected human. So in this talk, we will present a new type of model for the propagation of malaria. This new model has two distinct features. Both, first of all, the infectivity of an infected human, but also the infected vector, mosquito, varies with the time elapsed since infection. And when a human, after recovery, loses his or her immunity, that is progressive. Not the loss of immunity is not instantaneous like in most models in the literature. So let me first present the model for humans. So we will be given a collection of pairs of random functions having the law of the pair lambda gamma of t, which denote respectively the infectivity and the susceptibility of the given individual at time t after its infection. We assume that lambda is 0 for t negative, and that lambda is non-negative for all t greater than or equal to 0. Gamma is between 0 and 1. We assume that the sup of lambda of t is bounded. Okay, in fact, I'm pretty certain that I can just assume that this random variable is integrable. That should be enough, but okay, it's not completely written so far, so I prefer it's safer to say it's bounded. And moreover, I assume that the first time when gamma is strictly positive is is after the last time when lambda is strictly positive. Okay, and okay, in addition, we are given other, similar quantities with a different distribution for the initial status of the individual, but I will not detail too much about that. Okay, let me explain on a picture what I was saying so far. So suppose here 0 here is the time of infection, then the individual might first be exposed. So the individual is not contagious, not infectious during the first interval of time. Then its infectivity increases up to a maximum, then goes down back to 0. Then there is usually an immune period. And in the case where there is a loss of immunity, which is the case for many diseases, mostly, not all, but many diseases, particular COVID-19, but also the malaria, then after an immune period, the susceptibility starts to raise again and may converge to 1 or may converge to something less than 1. Okay, so most typical models assume that the susceptibility of the individual at the end of the immune period jumps from 0 to 1 instantaneously, but we will not assume that. Okay, so now we consider a human population of fixed size capital N. To each individual, K between 1 and N, we associate its initial status, which is summarized in the pair lambda K0, gamma K0. Okay, I don't want to discuss too much about this. It's not too important. But okay, now the number of reinfections of the individual K on the interval 0t is given by this integral. So now QK is what is called a standard Poisson random measure on R2+, which means it's a sum of Dirac measures at and those Dirac measures are located at random points, and the number of those points in any subset of R2+, any Borel subset, is its Lebesgue measure, and the numbers of points in these joint subsets are mutually independent. Okay, this is enough to characterize this Poisson random measure. Okay. Okay, so now you see you integrate over t, and when t increases, you encounter points of this Poisson random measure, and as soon as there is one point SU of this one Dirac measure in this QK is at a point SU which satisfies U less than or equal to the value just as S minus of this function, then the point is accepted and there is a jump of +1 in this, which means there is a new infection. Okay, now what is this mysterious function epsilon n k of t? Okay, there is a kappa, which is, okay, I will explain in a minute what is kappa, but it's not important. Now, what is important, the two important factors are the following. The first one, let me start with the last factor, which is the average is divided by NV, the average force of infection of the mosquitoes. Okay, the force of infection of the mosquitoes is exerted on the humans. Okay, this is the total force of infection of the mosquitoes. And then this is gamma, this is a susceptibility of the individual K. So as long as the susceptibility of the individual K is 0, then of course the individual cannot be infected. Okay, and the larger gamma, the more likely the person will be infected. Okay, what is this A and K of t? A and K of t is what I call the age of infection at time t of the individual, which means it's a time elapsed since the last infection. Okay, so it's t minus the largest s in 0t for which there is a jump of this function, which means that this is the time of the last infection on the interval 0t. And if there has been no infection, then this is 0, then this should be 0. Okay, so I think I've explained everything except I have not explained kappa. So N is a number of individuals. NV is roughly the number of mosquitoes. I say roughly because, as you will see, I have a I mean, there is demography. I mean, I'm not considering birth and death of the humans, but but I'm considering birth and death of mosquitoes. So the number of mosquitoes is not strictly fixed, but it's roughly NV. Okay, so kappa is the ratio of these two numbers. And we want to let both N and NV go to infinity, and we will keep kappa fixed. Okay, so by the way, just one word. I'm saying I'm not considering birth and death of humans, but you might object that, as I said on my first slide, malaria does kill individuals. So it's not fair to say there are no deaths of humans. Okay, but my assumption do not prevent that this function gamma could be 0 for all time with a very small probability. So when you pick, I forgot to say that at each new infection, this BNK of T increases by 1. So there is a new gamma kj. So all the gamma kj's are mutually independent. Okay. So when you choose a new gamma kj with a small probability, that function will be 0. If this function is 0, it means that the individual will never become susceptible again. It will never be infectious again, so it does not play any role in the epidemic. And we could also decide that could be the case of the deaths, those who die. Okay, so I have not explicitly written a status for death, but I could add it easily. Okay, now the total force of infection of the humans, which is exerted on the mosquitoes, is it is a renormalized total force of infection. So the total force of infection is this sum. Okay, you sum over all humans at time t. You take the infection age of the given individual, and you take its current infectivity. Okay, so of course, for many cases at any time t, for many cases it should be 0 because not everybody is infectious at any time. But okay, this is a general formulation, and then I'll divide by n, so I have a renormalized or rescaled total force of infection. And the renormalized total susceptibility, now this total susceptibility of the population at time t, it is quite similar, but I replace lambda by gamma. Okay, lambda is infectivity, gamma is susceptibility. So this is the infectivity which is exerted on the mosquitoes, and this is a susceptibility which is sort of the mosquitoes then attack those who are susceptible. Okay. Okay, so and then, as I said, those are ID copies of lambda gamma, and they are the ID copies of lambda 0 gamma 0. But I don't want to say too much about that. Okay, now this was enough for the stochastic model for humans. Now the stochastic model for the humans was what I call VIWI, which means varying infectivity and waning immunity. And the model for mosquitoes, it will be SI, which means susceptible infected, and VI, which is varying infectivity model with demography for the mosquito. So each mosquito has the infectivity lambda VI of T at time T after its infection. And the lambda VI, it it should be both L or both I. I'm very sorry. Okay, those are IID, and the initially infected mosquitoes have at time T the infectivity lambda V0 L of T L between 1 and the number of initially infected mosquitoes. Okay, in addition, susceptible mosquitoes are born at rate NV times mu V of T, and each mosquito dies at rate mu V of T. Okay, instead of NV, if you like, I should maybe put the number of alive mosquitoes, but if I do that, I have the problem that I would have a critical branching process which dies out in finite time. So I don't want that, so therefore I fix the birth rate at a certain rate times the size of population around which my mosquito population fluctuates. Okay, so each infected mosquito remains infected until its death. So there is no recovery. I mean, I talked with a medical doctor who has studied malaria, and he thinks that this is quite reasonable. Mosquitoes don't live very long, and they remain infectious for quite some time. So it's quite reasonable to assume this. Of course, I could change this assumption. It would not change too much the model, but okay, this is simplification which seems reasonable. And each mosquito gets infected at rate, okay, the resistance factor 1 over kappa times the renormalized force of infection of the humans, okay? And the proportion, so the proportion of susceptible individuals in the mosquito population is given like this. So I first take all the initially susceptible individuals in the mosquito population. But okay, sigma j is a death time, so I multiply by the indicator function that that individual is still alive, and this means that the individual has not yet been infected. Okay, the Cnj of t is similar to the Bnk of t for the humans, except that here there is at most one infection, but this process is 0 and as long as the individual is susceptible and jumps to 1 when it is infected. Okay, and then I have to add those who are born after time 0, okay, because there is demography, so there are the deaths, but there are the birth times. So alpha j, the alpha j are the successive birth times of mosquitoes, and I'm sorry, alpha L are the successive birth time of the mosquitoes, and sigma L is the corresponding death time. Okay, so the interval of life of the mosquito L is alpha L sigma L, and the mosquito is susceptible as long as it has not been infected. Okay, and the infection happens at this rate, as I said. Okay, so in fact, I have told you the proportion of susceptible, but I have to tell you what is the force of infection of the mosquitoes. So there are 3 subsets of infectious mosquitoes. There are the initially infected, those who were infected at time 0. There are the initially susceptible who get infected at some time, and then those who are born after time 0 and who get infected. So the total force of infection in the mosquito population is the sum of 3 terms. Okay, so it's renormalized. I forgot to say the bar means I divide by NV, the size of the mosquito population. So I take, this is the total. The first term is the force of infection, the renormalized force of infection due to the initially infected in mosquitoes. The second term is the force of infection of those who were susceptible at time 0, but get infected at some time tau and j. This is the jump time of the process C and J. So it's the infection time of the individual J plus the same, but now for those who are born after time 0. Then, of course, the time of infection, of course, is posterior to alpha L, the birth time. Okay? Okay, so now I want to state the law of large numbers. So I claim the following. So I want to take the limit in the above model as both n and nv go to infinity, while the ratio nv divided by n remains constant. So our main result reads as follows. As nv goes to infinity, those four terms, so I have included the kappa inverse here and the kappa here. So, but forget about those, they are not important. I mean, you could take the simple case where this is 1 and then they disappear. Okay, so you have first the renormalized force of infection of the humans. The renormalized, no, I'm sorry, the renormalized, oops, sorry, I said something stupid. The renormalized total susceptibility of the human population is the first term. The second term is the renormalized force of infection of the humans, which is exerted on the mosquitoes. Then you have the proportion of susceptible individuals in the mosquito population, and then you have the renormalized force of infection of the mosquitoes, which is exerted on the humans. Okay, note that here concerning the humans, I talk about the renormalized total force of total susceptibility, while here for the mosquitoes, I talk about the proportion of susceptible. Because in the mosquito population, each individual is either fully susceptible, so susceptibility equals 1, or fully immune. Okay, so the renormalized total susceptibility in the mosquito population is exactly the proportion of susceptible individuals. So there is no reason to make, I mean, they are the same. Okay, so this quadruple converges in probability locally uniformly in T to these four deterministic functions, h x h of t, y h of t, x v of t, y v of t, where x h y h is unique solution of the system of equations which I will give as the next slide, while x v y v is an explicit function of y h. Okay, so you have four functions. Those two solve an equation, a little complicated equation, and these are given as explicit function of YH. Now, let me show you the formulas. Okay, so the pair XH-YH solves the following system. So here, okay, those lambda bar 0, lambda bar, these are just the mean, the expectation. Lambda bar of t minus s is the expectation of lambda of t minus s. Remember that lambda is random. I mean, there are many copies of those, but they all have the same expectation. So when I take the expectation, which I write here with the bar, I don't need to put any index because they have all the same expectation. And this is the expectation of the lambda 0, the initial infectivity. Okay, so this is a proportion. This is the initial proportion of infected individual at time 0. This is the expectation of the initial infectivity function, and then this. Okay, you see that this is an integral equation. This is an integral equation, and in addition, this is a complete. This is not such a simple. I mean, this is a explicit formula, but a little bit complicated. I will give it in a minute. But let me first comment about the first equation. Okay, so first of all, okay, of course, XH, YH are deterministic. But what is random is both gamma 0 and gamma. These are random. So I have the expectations because I have to take the expectation of this complicated function of gamma, and here gamma 0. Okay. You see a big difference with this term here. This is expectation of lambda. It's just the first moment. So lambda in the limit, the random function lambda enters only through its first moment, its expectation, which is rather simple. While here, gamma enters the limiting equation, deterministic equation, through a complicated functional of gamma. And the reason is, okay, why does this exponential appear, this exponential function? You see, this exponential is, okay, suppose that an individual has been infected at time s. So this expectation is the probability that that individual has not been reinfected by time t. Okay, this is a probability of no reinfection, because you see when you look at those formulas. Okay, that was here. Okay, here you see in the okay. I was looking at the equation for the limit as n goes to infinity of that quantity. Okay, that's why it's reasonable to have a look at this again. Now you see that this function gamma, I'm not supposing it as a function of its last argument. You can think that it is increasing. I have not assumed it increasing, but on my picture, I put it as increasing. It's reasonable to assume that it is increasing. But you see that this is the time since the last infection. As soon as gamma is strictly positive, you can be reinfected. When you are reinfected, then of course this is replaced by 0. This jumps back down to 0, and then this gamma is 0, because gamma, after infection, gamma is first 0 for quite some time. You see this picture. Gamma is 0 from the time of infection up to here, gamma is 0. Okay, so you see it is very important here. Oops, so I was here. What is very important is that, okay, as you see here, in fact, lambda, here we don't have the same game, because for a new infection to appear, you need gamma to be non-zero. For gamma to be non-zero, you need lambda to be 0. So first lambda becomes 0, and then maybe you have a reinfection. Here it's not the same situation. Here gamma is increasing, and then suddenly you have a new reinfection, and you go down to 0, and the individual goes back to, the individual k then contributes to this sum, and so only later contribute again to this sum. Okay, so I don't know whether this clarifies, but I insist that the presence of these exponential factors and the fact that I have those complicated exponential of, the fact that I have expectations of complicated functions of gamma is related to what I was trying to explain a minute ago. Okay, so this is the pair of equations for x, h, y, h, but I have to explain you what is this v of yhs, which enters here, 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 and here. Okay, so it shows up everywhere. Okay, so now the pair xv, yv is equal to the pair s of yh, v of yh, where s of yh is, you see, it's a rather explicit function of y shows up here and here, but it's a given function, it's explicit, and it's no problem. And in fact, not only it is explicit, but it is easily shown that it is bounded, for instance, in fact, uniformly in time. This is very nice. But the next expression is really a bit more complicated. Okay, you see now this V of yt, you see you need first to have defined S in order to define V, okay? So V of yt, in fact, also is an explicit function of y, but much more complicated. First, you have to take, you have this functional which appears here, then you multiply by y. Okay, the first term is given, doesn't depend upon y, but this integral depends upon y. The second term depends upon y through that product of y by this S of y. Okay, so it's an explicit function, but not so simple. And that V again enters those this system of integral equations. So I insist also that this pair is not the pair XH, YH is not a solution of an ordinary differential equation. It is a solution of an integral equation, Volterra type integral equation. In particular, it has memory. Okay, it does not forget the past, unlike an ODE. Okay, so now, what do we prove? So I have stated a statement. What do we prove? We first prove that if I have a solution, then it satisfies a priori bounds on any compact time interval. Okay, this is very important because thanks to this, it's not difficult to show uniqueness, and also we can show existence by Picard iteration. But the Picard iteration is a little more tricky than uniqueness, because why any solution satisfies a priori bounds, it's not clear that the sequence in the Picard iteration satisfies the same a priori bound. So I use a modified Picard iteration to enforce those bounds, the same bounds that I was able to prove for the solution. Okay, anyway, and we can prove existence this way. So we have existence uniqueness of a solution to this system of equation. Now a very short, I will finish with, almost finished, and then some other comment. I want to say one word about the strategy of the proof of the low-range numbers. So I will say a word about the model for the humans. Similar thing has to be done concerning the model for mosquitoes, but explain it for humans. In fact, the most complicated is the one for humans. So I have already showed you this thing. Okay, I hope you understand roughly what is this Poisson on the measure. Anyway, this is a process which jumps by one. Okay, this process counts the number of reinfections. This is the rate of new infection, and this is the age of infection, which plays an important role because it enters here. Okay. Now, suppose I cheat. Suppose I cheat and I replace this annoying term, which is a complicated expression. Suppose I replace it by its limit as n goes to infinity. So as n goes to infinity, this quantity converges to yv of t, which is deterministic. So now, if we look at this, it is rather easy to see. Okay, now now you see I don't index those by n anymore. There is no index n. And in fact, you see that the B, okay, I forgot to say that the QK for various Ks are mutually independent. All the same law, IID, and they are independent. So now the BKs, unlike the BNKs, in fact, the BNKs, you could argue that they are exchangeable. Okay, maybe I'm not sure you know what means exchangeable, but okay. Anyway, in particular, the laws of the various BKs for various Ks are the same. But here we have much more. Here we have the BKs are IID. In fact, the pair BK-AK are IID. And those, in fact, what is more important, those gamma K of BK of T, AK of T, those are IID, independent, identically distributed. Okay? it's obvious because you see the only, okay, so this is deterministic now, unlike here, it doesn't depend upon the other blast. And here, this QK, those are IID. The QK is the only force of randomness for BK. The only reason why BK is random, why all those things are random, is because this is random. Okay, but they are IID for various cases, so those are IIDs. And now there is, so we construct an IID sequence to which we associate those quantities. Now recall that we have this. We have defined those, and those are the quantities which converge to the limit. Okay, there was a factor kappa inverse, but okay, it's not important. So we are taking the limit in those quantities. Now, if we cheat, we replace the BNK ANK by BK AK. Okay, everywhere, both here and here. Then I define what I call sigma tilde and h of t, f tilde and h of t. And now a classical functional law of large number tells us that locally uniformly in T, we have that those quantities converge, in fact, almost surely, better than my final result, which is in probability. I almost show convergence, and even locally uniformly in T. Okay, this is just the classical law of large numbers, except it's law of large numbers in some functional space of time. But okay, this is technical, it's not, but conceptually, it's rather standard. I mean, very classical. So now the two things that we need to show in order to conclude about taking the limit in Z pair, there are two things we still need to do. The first is that we need to check that you see what were the limits here in these low large numbers. We need to show that these are the same as the solution of our deterministic system of deterministic equation. Okay, this is some calculation. You just you multiply this by indicator B1 of t equals I and the sum over I, the same here. And you just have to compute. It's not too difficult. You can show this. And the next thing we have to do is, of course, we have cheated because we have replaced the bar by the tilde. We have to show that the difference between the bars and tilde go to 0 and then goes to infinity. Now this is in probability. This is locally uniformly in T. So this is okay. This is some it's a computation which takes several pages, which uses essentially clever estimates plus Gronwall lemma, and you can show this. And once this is shown, then the result is proved. Okay, we have to do the same also for, I just explained for the human population, you have to do the same for the mosquito population. Okay, so good. So well, I want to finish with some, okay, I know that you are starving, you want to go to lunch, so I will not be too long. Now, I want to say one word about some work in progress, which we have not yet done. Okay, we hope to find out under which condition there exists an endemic equilibrium in this model. Okay, now, there is a result which we have proved for the usual epidemic VIWI epidemic model, not malaria, but not vector epidemic, but the usual epidemic. It is the case that the proportion of infected individuals at equilibrium increases when we increase the duration of the progressive loss of immunity. If you like, if you go back to the picture here, okay, so okay, you could simplify by taking here, putting a straight line, okay, an oblique straight line, and then one. So if you compare between immediate loss of immunity and progressive loss of immunity, but of course with the same cumulative immunity, if not, we are cheating, then it is a fact. In fact, the first who noticed that are Tom Britton and Khalifi, then it is a fact which we have proved also that this increases the proportion of infected individuals at equilibrium, which also changes the proportion of people you must vaccinate if you want to avoid epidemic. Okay, so we hope to be able to show the same phenomenon holds true in the case of an epidemic propagated by vectors. Okay, I went a bit fast. I forgot to say that this joint work with Othman Baghdadi from Oujda in Morocco, and I want to thank you for your attention. Oops. Okay, that's it. Thank you. Any questions? Maybe I killed everybody, especially before lunch. No question. You are starving. You are eager to go for lunch.
Prof.
Hello.
Hello, sir. You're muted. We can't hear you.
Yes.
Okay, good. So thank you very much, Prof, for your presentation. So we want to engage you with questions based on your presentation, sir. All right. So are there people who want to ask questions from? Okay. 1, 2. Okay. 3. We are just going to take 3 questions. I don't know if there are people online. Please help us check. Participant online who might want us. Let's just take 1 or 2. So the first person. Okay, let's take the first question.
All right. Thank you so much, Prof, for that very rigorous math display there. I was just having a concern, two concerns. the way infectivity and susceptibility are alternating in that the formulation of that model, and because the model was particularly tagged malaria model, so that's why I'm a bit concerned, because I'm thinking of the biology of malaria, particularly when it comes to the human infection, the human part of the infection, which has to do about not just, so when the infection is not just in what food now, as what's aerosol. We know that when the gametocytes, when the human being is infected already, there are these two parts of the parasites, the merozoites and the gametocytes, and then the infectivity. I'm trying to see how the curve that was shown, that the infectivity, grows at the point and then wanes, and then finally the person becomes the susceptibility begins to now take effect. So I was looking at a situation where somebody can be asymptomatic in malaria transmission, and the gametocyte can be very much there throughout the person's lifetime if it's not treated, because even natural recovery can be very, very slow in that regards. So I was looking at how that concept will be able to bring into perspective the concept of presence of asymptomatic individuals that harbor these gametocytes much more and can stay longer. So where does that rising of the infectivity to the peak and then dropping, comes in that situation? That's one. Then it seems to also appear to me that this formulation may be good in an epidemic situation, where maybe the infectivity rises and then falls and then somebody becomes susceptible. In the case of malaria, I don't know how this thing comes in, considering the biology of malaria that is well established. Thank you, sir.
Okay, that's a good question. And unfortunately, I'm not at all an expert on malaria. So okay, let me show you again. Let me show you again my the picture which I had. Okay, so I mean, this is a sort of a general model which is not specific to malaria. I think that it is a fact that when you get infected, your infectivity is first zero. Okay, of course, this is much too long compared to the other interval, etc. I'm not. I mean, it's just a very rough schematic. I mean, schema, and okay, this period should be much shorter. But there is the exposed period, and then I think that intuitively that the infectivity raises more or less continuously, goes to maximum, and probably decreases. Maybe this takes very, very long time. And maybe in the case of malaria, the loss of, I mean, the infectivity lasts very long, much longer than for other diseases. And maybe the immunity could be, I don't know how long is immunity in that case. And okay, now, of course, one obvious criticism, which is true for all disease and maybe even more for malaria, is that you may expect that after having been infected once, the infectivity does not raise to 1. Okay, I have not assumed that. In fact, I mean, in my assumptions, gamma can do anything. In particular, I could converge to something 3 less than 1. But of course, if you have been reinfected several times, you expect that the number of times you have been reinfected, I mean, changes this curve. And I don't take this into account. I don't change the form of the lambda gamma after several infections. And of course, this is not realistic, but okay, if you want to do, okay, you can of course include the number of reinfection in your model. I think it has been done by my former student Brice Zossan Goufak with his collaborator Hélène Guérin. But okay, then the model becomes much more complicated and it's hard to deduce anything. In particular, when it goes to endemic equilibrium, it makes things very complicated. Anyway, I'm not sure I've answered properly your question, but that's all I can say. But again, I confess that I am not really an expert on malaria, and probably this model should be rediscussed with experts.
All right, thank you, Professor. All right, we'll take the second question. Okay.
Thank you so much, Prof. I am much more interested in the aspect of the stochasticity, that the advantage of the stochastic over the deterministic model, sir. Thank you.
I mean, what are the advantages of stochastic model? Okay, I can answer this question. Now, you see, okay, first of all, if you are looking at an epidemic in a small population, then clearly the situation is random. Situation is random, and no deterministic model is going to give a good picture of the reality. Also, at the start of the epidemic and at the end of the epidemic, when the number of infected individuals is a smaller order than the total population, in those two cases, you need to use stochastic models. And those two extreme cases, in fact, you can approximate by branching processes, but you cannot approximate by deterministic model. Okay, this is the first thing. The second thing is that, of course, there are so when you want to study, okay, all epidemic in all situations, okay, there are the situation of small populations where you need to use probabilistic models. There are situations where the population is large, but there are phases, in particular the beginning and the end of the epidemic, where you need to use stochastic models. Okay, and then there is another thing, that if you understand the stochastic model, you understand its deterministic limit, then you can also study the fluctuations. So the fluctuations can be studied using, for instance, the central limit theorem, but can also be studied using some more refined tools like large or moderate deviations, which is something a little more complicated. Anyway, there is one situation where clearly this question of fluctuation is important. It is a question of endemic situation, because in the deterministic model, under appropriate assumptions, the endemic situation is stable. So the endemic situation will continue forever. But in reality, in most real situations, sooner or later, I mean, the epidemic will stop sometime. Of course, it may take very, very long, and so maybe you don't see it. And it can depend upon the size of the population. So in fact, of course, when you are the closer, I mean, the larger the population is, the closer you are to the deterministic model. So but the stochastic model usually tells you that the endemic situation cannot be stable. Sooner or later, you will end in a situation with no disease anymore. Okay, but it may take very long to achieve this, and this can be studied using stochastic tools, to study the difference between the stochastic model and the deterministic model. Okay, I hope I've answered your. And for instance, I have when at the time when I was looking at Markov models, I have done this in a paper in Electronic Journal of Probability, where I used moderate and large deviation to study the time it takes to go out of an endemic situation. And now I hope to be able to do it in the more complicated models that I'm studying now. But this is a project with some students, but okay, we are only starting.
All right, thank you very much, Prof. All right, the first person. Thank you very much, Prof, for your presentation. Prof, I want to find out, for in case you are working on deterministic model and you want to consider noise, is it correct to convert the deterministic model to stochastic to incorporate the noise? Thank you.
Okay, this is a good question. I see many papers where people take deterministic model and they put noise somewhere and they study the new model with noise. I think if you put noise, you must justify where the noise comes from in reality. Okay, you just don't just put noise for pleasure in order to write a new paper. If you want it to make sense, you have to justify the noise term that you add that comes from some fluctuations in real life, in the real epidemic. Okay, so I'm not convinced by those papers where noise is added without any justification. I think you need to justify, to explain why you put a certain noise, why you put it in certain form, etc. It must come from real fluctuations which are in the epidemic and not something just to write a new paper.
Okay. Thank you very much. Prof.
Okay, thank you, Etienne, for your lecture. Yeah, Bob. I want to make some few comments because like what you presented has to do with epidemic, and like epidemic model for malaria, which means that you are looking at a scenario where malaria has not been in that environment, and then there is an outbreak. Epidemic means short outbreak, and then once there is a short outbreak, so we are not considering we have an adiabatic system where nothing comes in and nothing goes out, and that's what I saw from your demography in terms of the beds is equal to the death, so which capture the epidemic system. So and from this, we try to see that malaria in Africa is not more or less endemic. Let me put Nigeria for instance. It's persistent in Nigeria, and that kind of model may work in some systems where malaria curve has become flattened, and then there is an outbreak, and then we are trying to look at, okay, what is going to be what is going on. Now, the best approach, especially for an outbreak, is that at the beginning of the outbreak, I'm using a stochastic model because stochastic model will be much more useful because of the noise and the error, the noise. So at the beginning of an outbreak. So the best model to use is a stochastic model, which you have actually said. Now, we have had a situation in some of our work where we need to factor in some stochastic fluctuation because we are seeing, we want to fit a model, and then we are seeing that the data that was collected from routine data could have some observational error. And then because of the observational error, to really capture the pattern, we need to induce some stochasticity into the deterministic model, some parts of the deterministic, not just every part. The part you want to use to fit the model, we need to induce some stochasticity to be able to capture the pattern because we have seen a pattern that is different from seasonality. It's not seasonal, it's cyclical, you know. So, and it's because there are noise in the data, and then we need to capture. So, in line with what you said, it is not just about putting the stochasticity anyhow. It must be detected by the real situation. So we have a real situation we are dealing with currently, and that we have seen that the data collected have some observational error, like the routine data, people collect it haphazardly. So you cannot really trust, and then you find out that the pattern we are seeing is not having seasonality, is not showing any what's it called? It's showing virtually cyclical patterns. So, and then we need to introduce that kind of stochasticity to be able to capture the pattern we are seeing in the data, even though we are using a deterministic model, because for malaria in Nigeria, we cannot use stochastic model because it's no longer epidemic. It's only, or it's more or less persistence and is endemic. Now, the other person that said something the other time, you know, like when you talk about malaria in Nigeria, one major thing that has made malaria to be difficult to eliminate are the asymptomatic population, which happens to be 80%, roughly 80%, because these people don't go for tests, they are not sick. So they are moving in the environment, they live, but they able a large number of the parasites inside. And then when the mosquito, a susceptible female Anopheles mosquito bite them, they can pick malaria, and then the spread continues. So this kind of population are not captured because they are not. If I'm not sick, I don't go to hospital. You know, so that's the question. So it's only when you are diseased, you are down with malaria, you can treat. So now the challenge is that, you know, the 80% of which are the asymptomatic, they are not captured. Which in when we are talking about an endemic system, or like Africa, so your model does not capture what's going on in Africa. It only captures a system. Maybe probably now, as we are looking at Europe, in the next few years, we should, in Europe, because of climate change, we should be expecting some invasions of mosquitoes, female Anopheles mosquitoes. Now, because a lot of things will be changed. Let's say in the next 10 years, I think with that, your model is going to fit in to that kind of system. Over.
Thank you.
Okay, so let me just so let me see. Okay, you want to respond?
Yeah.
It's it?
Yes. Well, no, I understand. I have not followed all what you said, but I understand very well the question of if the proportion of asymptomatic people who are ill is important, then of course this is a very bad situation for controlling the epidemic. I understand very well. Yes. And then maybe of course, then you want to use some kind of stochastic model which tries to uncover these asymptomatic population. Okay, but I have not thought of this at all. But this is of course a very important issue, a very difficult issue.
Okay. Thank you very much, Professor Etienne Padu. I want to appreciate you for sparing part of your busy time to give this talk. We thank you for your time to prepare the slide and give this talk this afternoon. So we appreciate you so much. I was expecting you in Nigeria, but you have not come. You are still owing me a flight from Marseille to Lagos, from Lagos to Oye Ekiti. So I'm expecting you very soon, so that you will come and see us physically. Yes, so I want to, Etienne, you know, like I must say this, Etienne, I have known him for some time too, and I've been to his lab in Marseille, and we have put some things together on stochastic models, and he has also gave some of my students travel flights to free of charge. About how many of you? 5. Yeah, yes, 5 of my students free of charge to Ivory Coast when he was there. So I mean, we have done a long way, and I appreciate him. He's a professor emeritus in Marseille, AIX Marseille University, and he's still very strong, working very hard. You know, Etienne is strong, working hard, even over 70 years. I'm not sure Etienne should be around 80 now, right? Am I right? 80 years, right?
Yes,
Yes, he's 80. Etienne is 80 years. So he's very strong. So and I'm trying to follow him. What he's trying, the last time I asked him, I said, what do you do so that I can learn what you are doing so that I will also be strong by the time I'm 80 years. So you are still going to teach me more. Thank you very much. Can you give him a round of applause?
Thank you.
Thank you very much, Prof. Thank you. All right. So before we go for our lunch, I just want us to. Okay, Prof. Thank you very much. You can. Okay. Yeah. We can release you, sir, Prof. Thank you very much, sir.